Good morning, everybody. Thanks for coming to this session. I'm Sridhar Valaru. I'm Director of Product Management at ARM. I look after a number of IP development that I'm responsible for, but in addition to that, I'm also responsible for the security solutions at ARM. So today's topic was basically our journey of defining ARM's confidential compute definition from our product solution perspective. But as we are looking at solutions and exploring what are the different possibilities, there are questions that have come up, right? The things that you were trying to address in the previous two sessions, somewhat related to that, but they're orthogonal to just platform security. Our intent with this presentation was to talk through those challenges that we think will have to address as a community, and we wanted to raise that in this forum. So in general, when we were looking at the confidential compute problem, what were the threat models that we were trying to address? We were looking at primary motivation here was to make sure the user data and code are protected in the system. Right? When you look at a system that's deployed in a cloud, the threat is not just from outside adversaries. The data has to be protected from the hosted environment itself, right? So that basically means the higher privileged software have to be isolated from or prevented from having access to this data. So multi-tenancy is the other attribute of cloud environment. So that basically means you need to have strong isolation guarantees between the trusted virtual machines that will be running on the systems. And as we were talking about the threat models like physical access and so forth, you basically want to make sure the data that's residing outside where it's getting computed, in the sense your memory and so forth, the data gets encrypted. And because of multi-tenancy and so forth, you want to make sure each tenant has its own mode of encrypting the data. Accelerators are the other ones that are getting pretty prominent attention in the cloud environment. So that basically means when you are trying to use accelerators in a confidential compute environment, you want to make sure the data that's getting transferred from the host machine to the accelerators are protected as well. So all these frameworks are the things that we were looking at when we were defining our confidential compute solution. So before I go into what our confidential compute architecture looks like, just to give a brief history of how does security look like in an ARM system. So security in ARM architecture has been an evolutionary process. So we started off with TrustZone almost 10 years back. It's a fairly widely used technology where you have this partitioning of the system into two different domains. There's a secure domain and a non-secure domain. So secure domain is all where your privileged software resides. Non-secure domain was where user applications were running. And you have billions of machines. All the phones that are ARM-based primarily use this technology today. So as cloud systems were evolving, virtualization was added to the ARM architecture, right? So that basically provided different exception levels so you can have different layers of software in the system. You have a higher privileged software like hypervisor, which can manage the resources and so forth, and create the model where you're able to control how the applications are deployed on the machine. In the last 2 years, we've also, so one feature that was lacking, the hypervisor enablement was only in the non-secure domain. So that means all your secure domain was one big chunk of software code base that was residing there. In the last 2 years, we have introduced secure EL2. It's basically enabling virtualization in your secure domain. So now you have the ability to create this virtualized mode of execution even in secure domain. So you have different secure services from different parties in the ecosystem can be enabled on the same system, and they have the isolation guarantees that are provided in the virtualized environment as well. So one problem here is this non-secure address space is fully visible to the secure space, right? So that's from if you look at the confidential compute paradigm where you're trying to protect the user data, it fails in this domain. Similarly, the higher privileged software, hypervisor, for instance, which can allocate all the resources, has full visibility into where the application resources are residing. So to solve this problem, ARM is introducing a new extension called Realm Management Extension. So when you look at this model, it's an extension of the trust zone model that we were talking about, and create the isolation technologies to make sure now you have the ability to segregate the user data in a way that it's protected from all the other higher privileged softwares. So what happened in RME was the two world in the trust zone domain, secure or non-secure, each of them were partitioned into two. So what you see here is, if you look at the secure world, that was partitioned into two primarily because there are two kinds of secure software that your platform has. One is the firmware that comes with your platform boot and so forth, right? These firmwares don't change ever. But on top of it, people add secure services, like your debug and so forth. So we wanted to make sure there's an isolation between those two. So now the secure world is partitioned into two, so that way the code that resides in the monitor or the root world is the trusted firmware, which is open sourced, and people know what exactly it is before they're loading onto the machine. Then you have the secure world, where your secure services are added into the system. Moving on to the non-secure world, the non-secure world was now partitioned into two different domains. From a software programming perspective, these two look alike. The mode of operation is similar. So the programs that you have developed for non-secure world should seamlessly be able to execute in the Realm world too. So technically what happens is when somebody wants to run their application in a confidential environment, they request a Realm to be created. So there is a new entity called Realm Management Monitor, which is so in this particular case, the hypervisor still allocates the resources, but the resources security privileges are allocated by the RMM firmware. The RMM firmware is, again, just like ARM TFA, is going to be an open source firmware which partners can look at and audit and then provide criticisms if there are holes, right? So this is not some kind of a secret source, it's publicly available. And any conversation between the secure and non-secure, Realm and non-secure is communicated through the RMM. So that solves, and because RMM is the entity that's is providing the security attributes, nobody else in the system, even hypervisor, does not have the ability to override those attributes, right? So what that does is provides the isolation guarantees for the software layer that's running in the Realm. So it is protected from your secure and non-secure and any higher privilege software sitting in either one of them. The one world from which it doesn't protect is the monitor world. But the monitor world going forward, should be a very thin layer, and it's a firmware that's everybody should trust based on what we just learned in the last two sessions, right? So as we are looking at the platforms, the trusted compute base of the confidential compute, it does not include everything that's on the platform, right? It only includes the components in which come into the picture when storing the data. So your DRAM, for instance, is one of those things, because any compute, you're putting the temporary data in the DRAM and then fetching it back. As you're looking at attaching accelerators into the system, they also come into the trusted compute base. So how do you ensure that the data that's going outside your host are now protected? So that's where encryption comes into the picture. So these encryption keys are ephemeral. So that means any boot time, they're recycled every boot time or any time a VM is created. And this helps you make sure if the DRAM is outside and you're able to plug it out, it makes it harder for people to decrypt. Right? You have keys that are per session only. Similarly, for attaching I/O accelerators, you need to make sure the links are protected and the data that's inside the accelerators are also protected. So what goes in the accelerators is defined based on what kind of accelerators you're trying to attach. It could be PCIe or CXL, and there is work going on in those consortiums too, right? And as far as memory is concerned, memory is usually, DRAM doesn't have those capabilities. The host basically defines what kind of encryption technologies do you use to attach to these memories. In general, I think there is in addition to PCIe and CXL, there's a third consortium that is actively looking at what is required for confidential compute. The confidential compute consortium is the one that's driving some of the requirements on what the system should look like. So that basically means now there are 3 different bodies that are defining requirements in addition to OCP. Right? So how does somebody who wants to deploy their workloads on a cloud know that they're running on a trusted confidential compute environment, right? This is again based on attestation. The previous session we learned about attestation, but that was primarily for making sure the platforms are, the components going into a platform are trustworthy. But that doesn't mean me as a third-party customer for a cloud vendor know what's going on there, right? I need to be able to trust the system that it hasn't been tampered with, its state is still the same as what we were expecting and so forth. So when these requests could come dynamically. So these attestation reports will have to include the state of all the accelerators that are attached to the system, the host that's driving the system, and the infrastructure through which their entire data that's exposed is running. So technically, the way this works is there is a hardware root of trust built into the silicon in the host. The hardware root of trust makes sure it works after what the platform root of trust security service guarantees are managed. The hardware root of trust ensures that the realm management extension guarantees are adhered to before enabling the confidential compute. It's also responsible for making sure the manifests from the accelerators are also collected and be available to the end customer whenever, if they ask or demand the state of the system. All these things are collected by the cloud vendor and provided through their channels to the end customer. So the question that came up were, what are the scenarios that we have to think about when you're deploying the clouds, these machines in the cloud environment, right? So before I go to the concerns that we had, if you want more details, there are links to the confidential compute architecture and our work that we are doing out here, and you can also reach out to ARM using the address email address that's provided. So to end the call, to end this session, there was a call in the sense we are looking at, there are a couple of different problems that we think will be served better if we solve that as a community at OCP. Primarily, the consumers and the producers of this technology are in this room. So collectively, if we can put our thoughts together to solve some of these things, then the deployment of the generation of the systems will have some uniformity, and they will be easier to deploy. what are those things, right? Device attestation reports. So when you're looking at confidential compute attestation reports, with accelerators expected to proliferate, how do we make sure each of them are consistent in generating their manifests? And what are they doing in their devices to ensure they conform to the expectations of confidential compute? The checklist that was presented earlier today, that probably serves the purpose, but that may have to be expanded to look at what are the things that are needed in the confidential compute. Isolation guarantees and security concerns, again, from a hyperscaler vendor perspective, the platform requirements are defined today, and that's what the previous two conversations were about. But when you're trying to deploy confidential compute en masse, where non-technical companies, your financial industries and so forth, whoever wants to build their workload, bring their workloads onto the cloud, they want to see some kind of an automation to be done. And how do these reports look like? Lifecycle management and security certification, I think that's the other one that we have to ensure that the devices that are being built, they don't have security holes or vulnerabilities that come back to bite us in future. With that, I think that was my last slide. We have a few talks at OCP today. Please feel free to visit them. And we also have a booth in the exhibit hall. Please come and join us there. So any questions or topics?
Hi, Andres here. So going back to the previous slide, what do you have in mind when you're talking about security context same or smaller than virtualization contexts? When you're saying smaller, what do you have in mind? What are you trying to get at?
The virtualization context includes all the devices that are attached to it, right? Security context is you're only worried about where the data is exposed to, right? And you need to make sure those boundaries are only taken into account, right? You don't want to overcomplicate the system by adding too many attributes into this.
Okay. And then I had another observation. I don't know how much time we have, but there's a slide where you're showing the TCV and you're putting memory in the TCV. But what are the logs trying to signify there?
The logs are trying to signify that the data that's being placed in the memory are encrypted, right? So if it's a DRAM, DRAM doesn't have any controller capability, so you have to make sure the data is encrypted before it's going into the memory. As we are looking at, there's a CXL memories are coming into the picture. So the question is, do we trust the CXL device or CXL memory or not, right? Do we need to make sure the encryption happens on the host side? Or do we trust the device and use the security protocols that are being defined in the CXL and PCIe domain and use them to protect the media in there?
Okay, but I'm guessing just maybe I'm nitpicking here, but why would the memory, if it's receiving ciphertext, be within the confidential LET TCV? We're not really trusting it, right? I mean, we're trusting it not to destroy it, but
you have to make sure if there is so maybe my understanding of TCB is different, right? So when I look at these things, when I'm saying anywhere this raw data is sitting, it cannot be exposed, right? Once you're encrypted the data, the TCB probably shrinks in, but from a physical protection perspective, if somebody has access to the DRAM, are they able to get to your data or not, right? So from that perspective, the lines are blurry depending on what your definition of security guarantees are.
Well, do you have a CCA threat model that people can read? Because that would sort of.
I don't think there's a clear threat model identified. I could be wrong, but I'm not aware of one.
Right, because that could guide us.
Yep, definitely. I think those are the areas, that was the call to action, right? Okay. As to say, where do we draw these lines, and how do we make sure there's consistency across the deployments?
Okay.
Right. So currently, like I said, when the security work group at OCP seems like it's focusing on the platform security only, right? Having a subgroup or maybe a working committee to look at what are the additional subset of things that we have to look at to add confidential compute to the OCP security documents and so forth. That will be good.
That's your primary call to action.
That's my primary call to action.
Okay, thank you.
There is a threat model for CCA. I'm not sure if it's on the public site, but there is a threat model.
Okay. Any other questions? All right. Thank you all.